Alrighty, everybody. Welcome to today's lecture. Can you all hear me okay? Yes? No?
Yeah.
Yes. Thank you. Alrighty. Thanks so much for being here. I'm glad to see you all, and welcome to Lecture 10. This is our 4th week in the course, and I know that you guys have definitely covered so much information and you've worked so hard, but these next couple lectures I think are definitely going to cover a lot of the meat and potatoes per se of Chem 3570. So definitely make sure that you're coming to office hours and trying to stay as on top of the material as you can. I don't know if you saw Ashley's announcement last week, but we're opening up a new office hour that's Wednesdays 5 to 7. I will be there, and it would be great to see some of you all. So today we're going to introduce two important reaction mechanisms that we're going to be covering this week. They're called SN1 and SN2. We're going to talk about leaving group stability, and we're going to talk again about nucleophile stability. So the SN1 reaction is one of 4 main reactions that we're going to be talking about this week. I already mentioned that we're doing 2 of them today. And the mechanism looks a little bit like this. I'm going to draw my alkane. And it's got 2 different CH3s on it, a bromine and a hydrogen. Now, what can happen is that our leaving group, our bromine, can leave the molecule, creating a carbocation. Now, I know you guys have talked about carbocation stability quite a bit lately. So which type of carbocation are we looking at right here? If you want to type in the chat or unmute.
Secondary.
Yeah, it's a secondary carbocation. Great. So we have our secondary carbocation, which is decently stable. Not the best, but still pretty good. And I'll go ahead and add a nucleophile. And I'll show that attacking our carbocation to create a product. And there we go. This is our SN1 mechanism. We have our leaving group leaving, creating our carbocation, the nucleophile comes in and attacks, and we've got our product. So let's talk a bit about some of the characteristics for SN1 reactions. I know you guys have just finished 2080, so you've probably seen a lot of rate laws. This is the rate law for an SN1 reaction. K, of course, is the constant, and we've got this K out. This concentration of alkyl would be the concentration of our alkane that's in the reaction. So for the SN1 reaction that I drew earlier, the alkane would look like this with our 2 carbons and our hydrogen and our Br. So the concentration of that in solution, that's what the concentration of alkyl means. Now, would someone like to say what order this reaction is?
Is it second order?
It's actually first order. So I'll go ahead and write that it's first order. Because if you remember, I believe the rate law, like determining the order of a rate law, it's the amount of things that are in parentheses. So we only have one thing in parentheses here, or we have only one molecule in parentheses here that's dependent, that the rate is dependent on. So it's first order. And that's kind of how we get what the name of the reaction is. So it's abbreviated SN1, but it's actually called nucleophilic unimolecular substitution. That's where we get the name SN1 from. So it's called substitution because, as you saw, we substituted basically the OH for the Br, the leaving group. And it's called unimolecular because it's a first order reaction, and the only thing that influences the rate is the alkyl. Now, the rate determining step for this reaction is the formation of the carbocation. So if you're able to create the carbocation more quickly, for example, maybe it's a more stable carbocation, your reaction is going to occur faster. SN1 reactions only occur on secondary or tertiary substrates. And just a reminder that like secondary and tertiary substrates, those are alkanes, which if we deprotonated them, they would make a secondary or tertiary carbocation. So for example, this would be considered a secondary substrate because if you take off the bromine, then you would get a secondary carbocation, as we saw earlier. So I know I said deprotonated earlier, it's not deprotonated, it's removing the leaving group, removing the bromine in this case. And then for stereochemical outcomes of the reaction, we get what's called a racemized product. So we're going to get a mixture of enantiomers from the reaction. And I'll go ahead and draw that so you know what I mean. So let's do the same alkane, show the bromine leaving, we make our carbocation, which is secondary again, and then let's use a different nucleophile. I'll use NaCl, we've got the positive spectator ion, and the nucleophile is going to be this Cl- ion, which is going to go and attack our carbocation. And it's going to create two different enantiomer products. We can have one that looks like this, where the chlorine is on a dash, and we can have another where the chlorine is on a wedge, like this. And these are enantiomers. So it's important to note in this reaction that we will have the possibility for hydrate or methyl shifts since we have a carbocation intermediate. So I'll go ahead and draw a quick example of an SN1 reaction where we would have a hydride or methyl shift. So let me move this down a little bit so I have more room. And again, we have our secondary alkane, well, our secondary carbon that has our bromine on it, but it's adjacent to a tertiary carbon. So one that has more carbon substituents and is more stable. So if we have the leaving group leave and create that carbocation, we now have a secondary carbocation right here next to a tertiary alkane. So as we look at this, we can see that it's more stable to have our hydrogen over here move over to the carbocation, because if we do that, we're able to create a tertiary carbocation, which is more stable. And if we use the same nucleophile as before, let's say we have NaCl, that's going to go ahead and attack the new tertiary carbocation, and this will be our product. So here we go. Are there any other questions about nucleophilic unimolecular substitution? Alrighty, I will go ahead and move forward with the next slide. So a second substitution reaction that we're going to talk about today is called the SN2 mechanism. And it's pretty similar, but there are a couple of differences. So I'm going to go ahead and draw a primary substrate this time. still going to have the bromine on it. And I will draw our nucleophile, which will be SH minus. And last time we had the leaving group, which was bromine, leaving and creating a carbocation intermediate. But in this reaction, suppose we have our nucleophile come and attack the substrate from the back and kick off the leaving group and create our product. So now we can see that the substitution has occurred because in place of our bromine on the molecule, we have the thiol group. And we've got some Br minus floating around in solution. So this attack by the nucleophile, by the SH minus, is called a backside attack. Where else have we seen backside attacks in organic chemistry? Well, if anyone remembers last week's lecture, we talked about anti-reactions with the triangle intermediate, which can be backside attacked as well. So it's the same concept done in the SN2 reaction. So let's talk about some characteristics for SN2 reactions. The rate law here is second order, and it's equal to K times the concentration of the alkyl times the concentration of the nucleophile. So here, the concentration of whatever our nucleophile is very important because the reaction isn't going to be able to proceed without that backside attack. So for example, if I were drawing out the rate law for the SN2 reaction that I did earlier, it would be equal to K times the concentration of our alkyl, which would be this molecule, times the concentration of our nucleophile, which would be SH minus. And this is where kind of the full name for the reaction is from. So SN2 is the abbreviation for nucleophilic bimolecular substitution. So that's kind of where we get SN2 from. And it's second order, so two molecules where their concentrations control the rate. The rate determining step, as I kind of indicated earlier, is the interaction between the alkyl and the nucleophile. So the speed at which that backside attack occurs is directly related to how fast the reaction is going to take place. Now, in SN2 reactions, it's also important to note that we're going to have what's called inversion of stereochemistry. I know we talked about backside attacks last week, and you might remember that they also have inversion of stereochemistry on the attacked carbon. And what that just means is if I have a starting molecule that looks like this, draw my bromine, I'll put hydrogen back here. And let's say I have, again, some Cl minus as my nucleophile. If I attack this from the back and the bromine leaves, that just means that I'm going to end up with my chlorine on the back using dashes, and our hydrogen is going to move to the front and be on a wedge, sort of. And keep in mind that neither the example, I don't think, for stereochemistry here, or the example that I showed for SN1, neither of these molecules are actually chiral per se. I'm just using the examples to show you how the wedges and dashes would change. So the concept is the same, but none of these molecules are actually chiral. Also, for SN2 reactions, these are concerted reactions. So they occur with one step. There's the backside attack, and then the bromine leaves. So that's what concerted means. Now, if we have a reaction that's concerted, are we going to have to worry about hydride and methyl shifts? So the answer to that question would be no. Since our reaction takes place using one quick step and there's no intermediate where we could have a hydride or methyl shift, we don't have to worry about those, which is kind of nice. And then lastly, SN2 reactions can occur on methyl, primary, and secondary substrates. So we really want to avoid something called steric hindrance. And if I were to try to do an SN2 reaction on a molecule with maybe 3 methyl groups and a bromine, these 3 CH3s take up a lot of space. So it would be very difficult for a nucleophile to kind of get around and do a backside attack. So SN2 reactions aren't really going to occur on those types of substrates. And as we indicated up here, SN2 reactions occur fastest on less substituted substrates. So it's going to be fastest on a methyl substrate and then primary and secondary. And let me go ahead and cross out tertiary since those don't really see SN2 reactions very much. Are there any questions that I can answer about SN2 right now? Alrighty. That's occurring very slowly. Okay, so here we are again. Now we're going to go ahead and talk a little bit about leaving group stability because it's definitely a big part of both SN1 and SN2 reactions and later reactions that we'll talk about this week. So the best leaving groups are the large molecules that are stable with a negative charge. And these are qualities that you probably remember looking at last week when we talked about what characteristics would go into a good acid. For a good acid, you want to think about how stable the molecule is going to be when you take off the hydrogen and make the conjugate base, which is an anion. Here, we want to think about, is this leaving group going to be stable when I kick it off the substrate? And again, it's going to be an anion. So all those characteristics in the acronym AREO, those are probably going to come into effect. So keep them in mind. Most good leaving groups are weak bases, such as iodine, bromine, chloride, all those guys. And the larger and more polarizable they are, the better, just as with a good conjugate base. You want something that's large and polarizable. So we attach this little segment of the periodic table, and iodine down here is going to be a better leaving group than bromine, which is a better leaving group than chloride, because iodine is the largest and size is good at keeping them stable. As you also might remember from a characteristic of a stable conjugate base, good leaving groups will also probably have resonance, because if you have resonance, it's going to be easier to manage a negative charge. We're going to talk a little bit about solvents later on this week, but for now, just know that leaving groups aren't influenced by whatever type of solvent you have. And that's often something that has popped up on practice exams and exams before, where they throw in different solvents and say, which one is the best leaving group? And leaving groups are influenced by solvents, so just keep that in mind. And also, lastly, SN1 reactions especially need a good leaving group. And the reason, if you can remember, is that in SN1 reactions, the leaving group leaves by itself. So it isn't kicked off in a backside attack. So it's very important to have an especially stable leaving group for SN1 reactions, because that's the rate determining step, and it needs to be able to leave by its own and be stable so that you can get that carbocation intermediate. Any questions about leaving groups? Alrighty. let's go ahead and talk about some nucleophiles, if the screen sharing will cooperate. There we go. Can everyone see? All right.
Yeah.
Thank you. So, kind of as we were thinking about for a strong base, a good nucleophile is going to be an atom or molecule that is pretty unstable. So I've drawn here a list of the best nucleophiles, and I can't take credit for organizing this list since it was put out in a handout from a course called 1057, which is a supplement course for Orgo. And I definitely recommend trying to keep this list in mind because there will be a lot of questions in Chem 3570 probably where you have to rank nucleophiles from best to worst. So we'll go through and discuss these briefly. Our very best type of nucleophile is when you have a negative charge on a less electronegative atom. So for example, if I were to have a molecule like Cn-, where we have the negative charge on the carbon, carbon is a pretty electropositive atom, so it's not going to want to have that negative charge, and it's going to really, really want to attack another electrophile or an electrophile to get rid of the negative charge and form a new bond. So Cn- is a very, very good nucleophile, and it's at the top of the list here in terms of best nucleophiles. Now, another nucleophile, which is number 2, still pretty good, is when we have a negative charge on a more electronegative atom. So I showed this nucleophile before, but when we have OH-, that is not quite as good as Cn- because O is more electronegative. It's a little bit more stable with the negative charge, but still pretty good. And then our third best nucleophile is a lone pair on a less electronegative atom. So if we have NH3, keep in mind that these are all kind of relative terms, like when it says less or more. That's why this list is good to keep in mind if you have to rank nucleophiles. If we were comparing, let's say, nitrogen to oxygen, nitrogen would be less electronegative. So a lone pair on a nitrogen will be a better nucleophile than a lone pair on an oxygen. And then, of course, we have a lone pair on a more electronegative atom. So I'll draw maybe CH3OH, where we've got the lone pair on that oxygen, as we were talking about earlier. Because oxygen is more electronegative, this molecule is a little bit more stable and therefore a little bit less likely to go and attack something else. And then lastly, we've got our double or triple bond, which is what we were working with last week for alkene reactions. You will not be seeing these nucleophiles in SN1 or SN2 reactions. But they're still pretty relevant on our list. They're like the last in the order of best nucleophiles, so I thought I'd include them. And another factor in good nucleophiles that we need to keep in mind is steric hindrance. So over here, I have 2 different nucleophiles. One of them, however, has a lot of steric hindrance. I talked a little bit about steric hindrance earlier in SN2 reactions when I said that if you have a molecule like this with 3 different methyl groups around it, that molecule is not going to do an SN2 because it's got so much steric hindrance and you won't be able to get a backside attack. Well, the same is true for the nucleophile. A molecule like this, which has 3 different methyl groups attached to the carbon, it's going to be really hard for it to move quickly enough to do a backside attack. So this molecule, you see it's got the negative charge on the oxygen, so it should be up here with number 2 as our second best nucleophiles. This molecule, tert butoxide, barely even acts as a nucleophile at all because it's so sterically hindered. And then we've got our other nucleophile over here, much less steric hindrance, so it's able to fulfill its role in SN2 reactions. So steric hindrance is not great for nucleophiles, so keep that in mind. Sometimes it will be to your benefit if they give you the formula for a nucleophile and you have to rank it, to go ahead and try and draw out the structure and see whether steric hindrance is a big factor. Also, as we're talking about nucleophiles, I thought I would mention that SN2 reactions need to have a strong nucleophile. Would anyone like to unmute their mic or type in the chat and talk about why they think an SN2 reaction would need a strong nucleophile?
In order to carry out the back attack.
Yes, thank you so much, Arifa. Thank you. So because SN2 reactions need to do that backside attack, it's very important for them to be strong. So nucleophiles that you're going to be seeing a lot with both SN1 and SN2 reactions, I'll go ahead and star them. Probably number 2, which is our lone pair on a more electronegative atom, and you'll often see something like this, a lone pair on a more electronegative atom. Now, for SN2 reactions, you're gonna wanna have something that's more like number 2 than number 4, because number 2 is higher up on the list, it's stronger, it's gonna be better able to perform that SN2 backside attack. Of course, number 1 would be the best, but as we talked about, this is the most unstable, having a negative charge on a less electronegative atom, so it's not seen quite as often, I would say. For halogen nucleophiles and SN2 reactions, as I showed earlier, sometimes Cl-, I-, Br-, those can act as nucleophiles. The solvent determines whether a larger halogen or a smaller halogen is best, so don't worry about that too much for now, since we haven't talked about solvents yet. Just a list, as we said, strong nucleophiles would include like OH-, SH-, Cn-. These are all given in order of worst like I guess the worst nucleophile to the best nucleophile. But those are the nucleophiles you would want for a backside attack, as I said earlier. And then our poorer nucleophiles, those include things like H2O and CH3OH. As we talked about earlier, those are both in number 4. You probably would not want these molecules to do an SN2 reaction. In fact, you probably would see these more for SN1 reactions, since they can occur with a weaker nucleophile, since they don't need to do the backside attack. They just need something to attack the carbocation intermediate that's already formed. Are there any questions about nucleophiles right now?
I actually had a question. So usually when we talk about steric hindrance, right? I'm still kind of confused on how do you determine if a molecule does have steric hindrance if there's like no methyl groups. Let's say there are other molecules surrounding it. Like, how do you determine if it has a lot of steric hindrance?
That's a good question. I don't think in 3570 or in this course we would ask you to give you a random molecule and just say, hey, what's the steric hindrance on this, or is this sterically hindered? It's just good to keep in mind that in general, when you're ranking nucleophiles or trying to pick a nucleophile, the less sterically hindered you can pick it, or like the less groups are attached, to answer your question, the better. Like when you're looking at these 2 nucleophiles, do you see how one of them has more methyl groups attached than the other? Yeah. This one actually doesn't really have any methyl groups attached. So steric hindrance, I think it plays more in a role when you're like comparing nucleophiles for those ranking questions, or when you're like trying to do a synthesis problem like we talked about on Friday, and you're trying to decide which nucleophile to use. You want to pick something that has the less groups attached, or the fewest groups attached, if you can.
Thank you.
Did that answer your question?
Yes.
Okay. Alrighty, if there are no further questions, I'll go ahead and pass the baton on to Samantha.
I have one question.
Okay, go ahead.
So for the order, it's, so you have an electron on a more electronegative atom, and that ranks above a lone pair on a less electronegative atom.
Yes.
But why would that be the case? Because a nucleophile is one that donates its electrons to an electrophile, right?
Yes.
So why would it be better for a more electronegative atom with an electron? Like, why is it more likely that the second will happen than the third?
Why would it be more likely that, like, when you say the second, do you mean like this one versus?
Yeah, like why is it? Yeah.
Okay, well, this is like, I'm sorry if I like made it confusing. This is like just an order of the best nucleophiles. It like it's not an order of the most common nucleophiles. Was that something that you thought? Like, did you think that number 2 was more common than number 3?
Yeah.
Oh, well, this is just the order of like the best nucleophile. So number 1 is the best. And as I tried to mention, like CN minus, you probably will see OH minus, things like SH minus, those more common than stuff like CN minus, because CN minus is the most unstable, and unstable stuff is not necessarily great in organic chemistry. They make good nucleophiles, but they're not really energetically favorable. So number 1 compared to like number 2, and number 2 compared to number 3, those are just like an order of the best nucleophile, but I don't think it's necessarily like what's going to occur the most often. Was that your question?
Yeah, and then just to verify, the lone pairs, they're on an uncharged molecule, right?
For this purpose, yes, they would be on an uncharged molecule. Both of these molecules have a formal charge of 0.
Okay, thank you.
Did that answer your question?
Yes, thank you.
Okay. Anything else from anybody? Alrighty.
I have a quick question.
Go ahead.
This is the last part. I don't know if this is what she was trying to say, but I was confused about, again, like nucleophiles being electron dense specifically. Like I still don't really get why the ones with charges would be better than the ones with like specific lone pairs.
Can you say that again?
Like I'm not sure if this was her question, but I was unsure about why 1 and 2 would be better nucleophiles than 3 and 4 if like the definition of a nucleophile is something that's like electron dense or going to be like donating those electrons.
Well, do you understand that nucleophiles with a negative charge are more electron dense? Because the reason that it has the negative charge is because it's got a lone pair that it doesn't want to have. So these electrons, they do have a formal charge because they have so many electrons. These 2 molecules are both the most electron dense out of any on the list.
Okay, thank you.
Does that make sense?
Yes.
Alrighty. If we have other questions in the interest of time, let's try and save them for the end of lecture so that we can make sure we get through all the material.
Hello, it is me again. Thank you, Sydney. Let me screen share. Can everyone see this?
Yep, looks good.
Thank you, Sydney. So something we want to talk about is, let me get rid of the faces, is the difference between nucleophiles and bases, because I know we've been talking about, both of those are really small highlighter. We've been talking about both of them a lot, and it's pretty easy to get them confused just because sometimes they will have similar qualities. For example, like a good nucleophile and a good base both tend to be pretty unstable, whereas like bad ones are both more stable. So what you want to remember is that nucleophilicity is a kinetic property. So it's going to be a measure of reaction rate because remember, kinetics is going to be like the energy of motion. So you want to be thinking how quickly could this atom or molecule or ion or whatever have you attack something. And on the other hand, basicity is going to be a thermodynamic property. It's going to be related to pKb, pKa. And when you think about basicity, you want to think about how stable is this atom or molecule or ion or whatever with negative charge. And if you remember the Bronsted definition of a base, that's going to be, I forgot to write base, there you go. That's going to be an H plus acceptor. So a weak base is going to be more stable with negative charge, aka it's less likely to take the H plus. And as you're going to see soon, some molecules can act as both nucleophiles and bases, while others are just going to act as either a good nucleophile or a good base. And so molecules which are only bases generally aren't going to be relevant to the two reactions we were talking about today, but they are going to be important on Wednesday with Buffon, the queen herself. So stay tuned for that. Gonna keep going. And so there are some guidelines for nucleophilicity and basicity that might help you out. And you're going to often see problems like in 3570 and to some extent 3580 that are going to be like, rank these nucleophiles or rank these bases based on their strength. And so here's a quick tip to remember this. And this is going to be for non-halogens, so I'm just going to cross them out, pretend they're not there. So for nucleophilicity, or for the same row, let's scroll down there. They're going to follow the same trend. So atoms in the same row are going to follow the same trend for nucleophilicity and basicity. So for example, if we were to look at nitrogen, is that going to be more electronegative or less electronegative than oxygen? Anyone want to shout it out?
Less.
Less, thank you. Nitrogen is going to be less electronegative. I'm just going to abbreviate it EN. Oxygen is going to be more. So if we were to look at, for example, H2N minus and OH minus, we're going to see that N is less electronegative. That means it's less stable with that negative charge. Therefore, it's going to be both a stronger base and a stronger nucleophile than OH. And so on the flip side, we're going to look at same column. You're going to notice that for the same column, it's actually going to have the opposite trend for nucleophilicity and basicity. Remember that size is going to increase going down. So sulfur is going to be larger than oxygen, whereas oxygen is smaller. And so if we want to look at, for example, OH again, and let's do, that was a weird O, SH minus, we're going to see that S is larger than O, and so larger atoms are going to be more stable, aka weaker bases. So OH is actually going to be the stronger base. But because S is larger, it's going to be a better nucleophile because it's more polarizable, sorry, I have one brain cell, than the smaller atoms. So this is going to be a stronger nucleophile. Does that make sense? These two guidelines are really good. I think Sydney actually put them there, so thank you, Sydney. But yeah, these are really helpful. Remember, again, no halogens for now. So now we're going to do a lot of practice, our favorite thing. And so we want you to figure out which leaving group is the best. In this case, we're now working with halogens. And if you remember what Sydney said, the larger atoms are going to be the better leaving groups because they're more polarizable. So this goes smallest to largest. Remember, size is going to increase as you go down. And so the largest guy here, you're going to see him at the bottom. Of course, it's going to be iodine, iodine ion. Then it's going to be bromine, then fluorine. Remember, he's the largest. He's going to be the most polarizable. And that's why he's the best leaving group. So on to the next one. Now we're going to rank the following nucleophiles. And here's something that I found a little bit interesting. So sometimes, like we're talking about, nucleophilicity will follow similar trends to basicity. So if we were to look at the two guys on the left, we're going to see that H2S, his conjugate base is over here, the SH minus. And so we'll actually see that SH minus is both a better base and a better nucleophile. I'm just going to draw the lone pairs here just so you remember. And so we know this much at least, but we don't know about these other two. So we're going to have to look at the rules that Sydney talked about earlier. Let me know if this is too small for any of you and I can write it bigger. I'm just going to write 4 of them because we don't need the 5th one for now. So first one's going to be negative charge on a less electronegative atom. That's why I wrote the downward arrow. That's going to be negative charge on a more electronegative atom. And then 3 and 4, which are lone pair on less electronegative, lone pair on more electronegative. And remember, these guys generally are going to be uncharged. I think the last one is double bond or triple bond, but we don't need to worry about it for this problem. And so we're going to look at these guys. And between sulfur, oxygen, and fluorine, which one is the least electronegative? Does anyone want to shout it out?
Sulfur.
Yes, exactly. Thank you, Arifa. It's going to be sulfur. So this guy is going to be number 1. Oxygen is going to be less electronegative than fluorine. So 2 and 3. This last guy is going to be 4. And you might be like, okay, what the heck? Like, he is a sulfur, though. Just remember that he is also uncharged. So he's going to fall down here around 3 or 4. He's the only uncharged one, so we're going to go ahead and put him on 4. I'm going to keep going. We're almost there. I think we have 4 more guys. So for this one, we're actually going to do a reaction. So we have our solvent here. It's going to be NaOH. And if you remember from Gen Chem or 2080, this is going to be a strong base. It's going to dissociate pretty readily in solution. So you can just imagine this as OH minus. You guys know that the negative charge is actually on the oxygen, but I'm just going to draw it there. And so this is going to be a good nucleophile. If my thing wants to draw. And so do you think this is an SN1 or an SN2?
SN2.
Exactly. Good nucleophiles are for SN2. SN1 can generally happen with a poor nucleophile. And so something you want to check real quick is the following. That you're working with a substrate that's either a methyl, primary, or secondary. I'm going to move them up here for space. No, I'm not going to move them. I'm going to move them. And so we're going to look at our guy on the left. And so this is the carbon he would be attacking. And if he were a carbocation, he would be primary, secondary. So we're okay. And so what we're going to do now is do our backside attack. I'm going to go ahead and draw the OH over here just because it's easier. And A plus is just floating around. Remember, it's going to be a backside attack. I'm going to go ahead also draw the hydrogen in there just for later. Does not super matter though. Backside attack, kick off that bromine, and your final product will look something like this. I'm going to draw it backwards, and I will show you guys in a second why. It's going to have to do with the inversion of stereochemistry. So dash, 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 wedge, dash, dash, dash. And remember that this is going to be a concerted reaction. So it's one step. We don't have to worry about any kind of methyl shift or hydride shift or something. And the reason why I drew it like this is to show the inversion of stereochemistry. It's kind of a pain in the butt when you're doing SN2 and you have like these long alkane chains. I'll show you an example where the inversion is more obvious. And you can go ahead if you wanted to and check the stereochemistry by doing your favorite thing, R&S configurations. So if we looked at the guy on the left, the spread carbon again, we're going to see that the priority goes something like 1, 2, 3, 4, and that is going to be S. And so we go to his friend on the right. That's the same carbon. We just flipped him. 1, 2, 3, 4, and he is going to be R. And so, yeah, you're going to see that we went from S to R. So we very successfully, I don't know why I said very, we successfully inverted the stereochemistry. Any questions on that so far? If you want me to, if you stay tuned after class or in office hours, I can try to draw the inversion, keeping the alkane chain on the left, but right now it's not even 9 a.m. and I don't have enough brain cells to do that. So yeah. Here's going to be another practice. And so again, we want to start off by looking at our solvent. We have H2O. That's going to be a bad nucleophile. And so what do we think that is? SN1 or SN2? It's going to be
SN1.
Yes, thank you, Nestor. It's going to be SN1. So I'm going to go ahead and draw in the hydrogen just for kicks. And let's check our methyls real quick. You always want to, well, not your methyls, sorry. You want to check your carbons real quick. These were carbocations. This guy would be, in the red, would be secondary, 1, 2. Guy in the blue would also be secondary, 1, 2. And so in this case, there are not going to be any methyl shifts or hydride shifts. You always want to check this with the SN1s because that's where it could happen because you have your carbocation intermediate. I'm going to go ahead and just draw the products for now, just for the sake of time. But if you have any questions on how I got this, I can also show you. I'm going to add your OH, and then you're also going to have his buddy. Remember, this is always going to be a racemic mixture. And like I think Sydney might have mentioned before, and definitely in previous lectures, you can usually also just write plus enantiomer. I would check with your professor before your exam, but generally they're okay with you just writing like plus enantiomer. You could either drawn like this guy and been like plus enantiomer, or drawn him and written plus enantiomer. It doesn't really matter. This is going to be a racemic mixture. This is our products. And then we are almost there, last two. So it's going to be the same guy again. I'm going to draw on the H. This time we have a different base. So this is kind of one of the funky ones. I honestly think I just might have memorized this one. It's actually going to be both a really strong base and also a really good nucleophile. So this is going to be SN2. We want to double check that we're not working with any tertiary or quaternary substrates. So we can just look at these guys real quick. Now let's make him blue. You're going to see this is secondary. He's also secondary. That's not so important for now. But yes, so we are all good there. We can do our SN2. And if you remember, it's going to be a backside attack. I'm going to draw my CMIS here. BR is going to go off. And your product is going to look like this. And so this is what I was talking about, where these instances of SN2 reactions where it's easier to show the inversion of stereochemistry, you can see that where the BR got kicked off, that went from being a wedge to now being a dash where the CN is. And then the hydrogen, that's the same hydrogen. He just went from being a dash to being a wedge. So usually when you have SN2, it won't be like that ugly, like long alkane chain. Otherwise it's a pain. Yeah. If we want to, we could do the R and S stereochemistry, but in this case, I think it's a little bit easier to see that this has been inverted. Oop, here's our last one. Pretend you didn't see that.
I have a question for
Yeah.
the one before. So you don't have to flip the chain?
Um,
You do that.
And the other way you can do it is,
Right.
that's a good question. Thank you for asking. Let's see. If you drew it like this, that should be the same thing.
Oh, okay.
Does
All
that
right.
make sense? So these two are going to be equivalent.
Oh, got you. Okay.
So you can do it either way. I think sometimes it is easier to just flip the chain. Like if you see the other guy, this
Mhm.
bromine did not start off on like a wedge or a dash.
Yeah,
So
that's why I got confused.
yeah, thank you for that question. Yeah. Does it make sense to everyone why these are the same molecule? We just turned them around. So the last problem can be this guy. So CH3OH, this is going to be one of your other weird solvents. It's going to be a bad nucleophile. This is going to be SN1. So like with all SN1s, we want to check our carbons. This guy in the red, this guy in the blue. He would be quaternary. He's going to be secondary. Yeah. 1, 2, and then 1, 2, 3, 4. And so what's going to happen here is what? So we're first going to show this chloride coming off. And it's going to look something like this. And does anyone have an idea what's happening after this?
A metal shift?
Yeah, exactly. So it's going to be a methyl shift. Remember that these are a little bit more uncommon than hydride shifts, but for example, if this guy on the left in the red were tertiary instead of quaternary, we could probably just take one of his hydrogens. In this case, we only have a quaternary, so we have to take a methyl. So remember your Cl is just vibing out there. And once we do the shift, we're going to get the following. So this guy in the blue, let me label him. The guy in the blue is no longer going to be a carbocation. He's now tertiary. This guy is also tertiary in the red, but he's now the carbocation. I'm just going to show this as an intermediate. And so now we're actually going to think about our solvent. Finally, he is going to come in and attack. You're going to get something like this. It's going to look ugly. You get OCH. And get the other, I'm going to put the other H up there. That's going to be plus charge. And you want to go ahead and deprotonate him like we do always. So what this lets me just take off that plus charge by taking off that proton, and your final product is going to look like a less ugly version of that. That's still ugly. Oh well. I'm just going to put your OCH here. I'm going to put them up here. Does that make sense to everyone? I moved him up, but it's the same thing. You just imagine I had him up here instead. Anyone have any questions on that? That is our last practice. So if you guys don't have any questions, that's the end of lecture. Anyone have any questions for me or Sydney? I'm just gonna vibe here for like 5 more minutes, but
Oh, hi. Do you mind going over your third to last slide? Just like showing.
sure. 1, 2, 3. This guy?
Yeah.
So do you want me to just go through the whole thing again, or?
I guess if you could explain the products, how you got that again.
Yeah, so I don't know why my brightness went down. Let me put that up. Remember, this is going to be an SN1. We're going to get that carbocation intermediate. So if we want to first just take off that bromine. Just going to draw them down here. We're going to have that H there, but I'm just going to put them like this. Then you have your H2O. Let's do. He's going to come in and attack. This is going to be our carbocation intermediate right here, because remember, SN1 is not going to be concerted. It's going to be multiple steps. So after that happens, you get something that looks like this guy. My stereochemistry looks a little bit whack right now, but I'll fix that. He's going to be plus charge, and we're going to have to come in again and deprotonate him. And so you should end up with something like this. And that's going to be that same guy who's over here. And if you remember with SN1s, you're always going to have the enantiomer because you're going to have a racemic mixture. So that's why I just drew the mirror image over here. Does that make sense?
Yeah, thank you.